Hi, I'm Herb Gross, and welcome to lecture number 22 in our series Gateways to Algebra, where today we'll conclude our introductory discussion of simultaneous linear equations. What I wanted to do today was first finish up part of the topic that we were discussing last time, and secondly, get to the situation where we deal with higher dimensional systems. In other words, what I'll do later is deal with a system of three equations with three unknowns, just to show you one of the things that we do over and over and over again in logic. Algebra, from that point of view, is nothing more than an application of logic. And what we're going to do over and over and over again in logic and in the algebra is every time we come to a new problem, we're going to try to find a way to reduce it to a previous problem that we've already learned how to solve. But before we get into that, let me just make a few more remarks about systems of equations, even when we're just dealing with two dimensions. I think when we ended last time, we were dealing with the equation that was 0.08x equals 0.05x plus 300. A lot of people, for some reason or other, even though it's an algebra course and arithmetic is a prerequisite to algebra, some people still have trouble with problems that have decimal points in them. Whenever that happens, keep in mind that you can always multiply both sides of an equation by the same number without changing the solution set to the equation. So for example, notice that to turn 0.08 into a whole number, you'd want to move the decimal point 2 places to the right. That would also turn 0.05 into a whole number. Now, to move the decimal point 2 places to the right is the same as multiplying by 100. And what the rule says is you can't multiply part of an equation by 100. What you can do is what? If you multiply both sides of the equation by the same number, you see, then you can do that. So if I multiply both sides of this equation by 100, see what that does? The left-hand side becomes 8x. The right-hand side, and I have to be careful here, I'm multiplying the whole right-hand side by 100. The 0.05x becomes 5x, and the 300 becomes 30,000. And now do you see what's happened over here? This becomes a whole number problem. And now, in this, see, this problem here is exactly the same, meaning it's equivalent to this problem over here. But the difference is, if I don't like decimals, this problem here does not psychologically scare me, whereas this form here might. So if I don't want to work with this form, all I have to do is what? Multiply both sides by 100 and just work with this form over here. And by the way, the same thing happens when you're dealing with fractions. For example, suppose I had a problem that said, if you add a half of a number to a third of the number to a fourth of that same number, the answer is 65 over 12. Now, if you're afraid of fractions, do you see how scary that problem there looks? But what is the common denominator for 2, 3, 4, and 12? Don't 2, 3, 4, and 12 all go into 12? So what I can do is what? To get rid of the fractions here, I will multiply both sides of the equation by 12. If I do that, see what happens? The 12 multiplies the 1/2 to give me 6. The 12 multiplies 1/3 to give me 4. The 12 multiplies 1/4 to give me 3. In other words, by multiplying both sides by 12, look what happens over here. I get 6x plus 4x plus 3x, and the 12 multiplies the 65 over 12 to give me 65. And what do I wind up with? 6x plus 4x plus 3x equals 65. Okay? And what's interesting is this problem here is equivalent to this problem over here, but the difference is there are no fractions in this problem. This just says what? 13x is equal to 65, so x is 5. I'm not going to take the time to check this, but what this says is what? Half of 5 plus 1/3 of 5 plus 1/4 of 5 turns out to be 65 over 12, and if you don't like that particular name, that's also the same as what? 5 and 5/12. By the way, the same thing happens if you're given simultaneous equations. See, suppose I said to you, I'm thinking of two numbers, and you said, give me a clue. I say, okay, 3/2 times the first number plus 2/3 times the second number is equal to 1. And 4/3 of the first number plus half of the second number is equal to 7. Now, do you see the fear of fractions over here? If a person is afraid of fractions, how am I going to handle this? Well, again, notice that the common denominator of the first equation is 6. Also, by coincidence, it also happens to be 6 for the bottom equation. That wasn't so important. The important thing is there's a common denominator for both of these. Just happens to be 6 in both cases. So multiply both sides of each equation by 6. See, 2 goes into 6 3 times. 3 times 3 is 9. 3 goes into 6 twice. 2 times 2 is 4. Okay? So when I multiply the top equation by 6, I wind up with what? 9x plus 4y equals 6. Multiply the bottom equation by 6. 3 goes into 6 twice. 2 times 4 is 8. 2 goes into 6 3 times. 3 times 1 is 3. And 6 times 7 is 42. So if I multiply both sides of the bottom equation by 6, the bottom equation becomes what? 8x plus 3y equals 42. Now look at the psychological difference between this and this. This one will scare you if you're afraid of fractions. Here is an equivalent system without fractions. And by the way, just by way of review over here, how would we solve this system? Well, for example, to get rid of the y's, since there's a 4 here and a 3 here, multiplying the top equation by 3 and the bottom equation by 4 would give us a 12y in both equations. What happens over here? 3 times 9x is 27x. 3 times 4y is 12y. 3 times 6 is 18. 4 times 8x is 32x. 4 times 3y is 12y. 4 times 42 is 168. Now, if I want to get rid of the y's, since 27 is less than 32, I'll multiply the top equation by -1, change the signs there. Now what happens? A negative 27x and a positive 32x is 5x. Negative 12y and positive 12y drops out. Negative 18 and positive 168 is positive 150. And if 5x equals 150, x must be 30. Okay? Now, once I know that x is 30, I can replace x by 30 in this equation over here. 30 times 9 is 270, plus 4y equals 6. Subtract 270 from both sides. That says 4y is 6 minus 270. That says 4y is minus 264. And that says what? That y is equal to negative 66. And by the way, again, in math, you don't have to take my word for it that this is the right answer. If this is the right answer, what should happen? If I replace x by 30 and y by negative 66, both of these two equations should be true. And let's see if that works. I replace x by 30 and y by negative 66. What happens? 2 goes into 30 15 times. 15 times 3 is 45. Okay? 3 goes into 66 22 times, so that's negative 22 times 2 is negative 44. 45 plus negative 44 is positive 1. That checks out. 4/3 of 30, 3 goes into 30 10 times. 10 times 4 is 40. 2 goes into 66 33 times, but since this is negative 66, the answer is negative 33. 40 plus negative 33 is positive 7. That one checks out also. Okay? So you follow what we're doing so far? You see the idea? What's nice about inequality is what? If you have denominators and don't like fractions, just multiply both by the common denominator, and you can convert the problem from what? One that you're uncomfortable with into one that you are comfortable with. And by the way, we do that in our everyday life. That many, many times when we're faced with a certain situation, we try to do it what? Break it down into a series of more pleasant tasks or less unpleasant tasks, and then hopefully string them together to get the same job done. And again, what we're going to find happens that even when we do this, sometimes we wind up with situations where even our best efforts don't solve the problem. Let me give you another example here. Suppose I tell you I'm thinking of two numbers. And you say, okay, give me a clue. Okay? And I say, okay. If I add the two numbers, the answer is 10. And if I take twice the first plus twice the second, the answer is 20. Okay? Now what's interesting is it sounds like I've given you two pieces of information. But look what happens over here. Let's see. What I'm going to do is I'm going to double the top equation. I'm going to multiply both sides by 2. So what do I get over here? Okay? I get what? 2 times x is 2x. 2 times y is 2y. 2 times 10 is 20. So the top equation is what? 2x plus 2y is 20. The bottom equation is 2x plus 2y is 20. Now when I subtract, what happens? 2x from 2x is 0. 2y from 2y is 0. 20 from 20 is 0. lo and behold, I get 0 equals 0, which is always true. In other words, somehow all my variables dropped out over here. And what happened was, here's another thing that happens in life. You think you're giving a person two pieces of information, but in a disguised form, what you've done is what? You've given him the same piece of information twice. You see, in reality, what happens is, if you try to draw the graph of x plus y equals 10, how does that graph look? When x is 0, y is 10. When x is 0, y is 10. And when y is 0, x is 10. So the graph of x plus y is 10 looks like this straight line. Now how would you graph 2x plus 2y? When x is 0, y is 10. When x is 0, y is 10. That's still the same point. When y is 0, 2x is 20. That says x is 10. This is the same point. Both of these are what? Two different ways of stating the same relationship. By the way, sometimes something even worse happens. See, suppose I said to you, I'm thinking of two numbers. And when I add the two numbers up, the answer is 10. But if I take twice the first plus twice the second, the answer is 24. You say, oh, well, let's multiply the top equation by 2 again. I get what? 2x plus 2y is 20. The bottom equation is what? 2x plus 2y is 24. Now I subtract the bottom from the top. And what do I get? 2x take away 2x is 0. 2y take away 2y is 0. 20 take away 24 is negative 4. Well, how can 0 ever equal negative 4? That statement is never true. Now what I've done is something worse. You know what I've done now? I've given you contradictory statements. And that often happens in our lives in the real world. You know, if somebody tells you to do one thing and somebody else tells you to do something that's incompatible with that, how can you possibly do both of them? So sometimes you have to make a value judgment as to which one you're going to obey and which one you're not going to obey, or else there's going to be what? No solution. It would be like in baseball, if 3 strikes was an out was one rule, and 4 strikes is an out is another rule, then the first time somebody has 3 strikes, the game is over. Because one team says 3 strikes is an out, the other team says 4 strikes is an out, and the umpire can't resolve the difference because they're both right. You mustn't have contradictory situations in a given situation. I just want to just get rid of something over here for a minute. And what I'd like to do is just show you again what happened over here. See, what happened over here was this. When we said x plus y was 10, by the way, if x plus y is 10, doesn't 2x plus 2y have to be 20? See, how could it possibly be 24? What happens in terms of a graph is this. When you graph x plus y is 10, we've already seen that. That goes through the points 0, 10, and 10, 0. That's a line like this. The graph of 2x plus 2y is 24. Watch what happens. When x is 0, 2y is 24. That says that y is 12. So the second line goes through the points 0, 12. Also, when y is 0, x is 12, so it goes through 12, 0. Do you see what happens? The graph of the second equation is what? Parallel to the first one. They're 2 units apart over here. And you see what's happening? These two lines will never meet. In other words, what's happened is, for this to be true, you have to be on this line. For this to be true, you have to be on this line. And since these are parallel lines, you can't be on both lines at the same time. So here's a situation where what? In the guise of giving you 2 sets of conditions, 2 conditions, right? I gave you contradictory conditions. They can't both happen. And sometimes we have to be able to recognize when both things can't happen. Well, anyway, that's enough as far as 2 equations with 2 unknowns are concerned. Let me take the remaining 10 minutes or so and introduce you to how we tackle problems involving, say, 3 dimensions, where I give you 3 pieces of information. See, let's start with a fairly easy example. I mean, what I mean by easy example is one where I give you the answer right away. See, suppose I tell you I'm thinking of 3 numbers. And you say, give me 3 clues because you're thinking of 3 numbers. I say, okay, here's the clues. The first number is 2. The second number is -1. And the third number is 3. Well, how much better clues can you want than that? What are the 3 numbers now? X equals 2, y equals -1, and z equals 3. That's explicit. Let me see if I can't give you an implicit relationship instead now. Suppose I say to you, okay, if you add the 3 numbers up, the answer is 4. Do you see where I got that from? See, 2 plus negative 1 is 1. 1 plus 3 is 4. Is that a true statement? Yes, if I add these three numbers up, it's 4. If I take twice the first number, that's 4, right? Twice 2 is 4. 3 times the second, that's negative 3. 4 plus negative 3 is 1, okay? 4 times 3 is 12. 1 plus 12 is 13. You see what I'm doing? I'm computing different combinations of these and telling you what the answer is. For example, 3 times 2 is 6. 4 times negative 1 is negative 4. 6 times 3 is 18. 6 plus negative 4 is 2, plus 18 is 20. So here are these three conditions. So now I say to you, not this. I say to you, I'm thinking of three numbers. You say, give me 3 clues. I say, okay, if you add the first and the second and the third, the answer is 4. The second clue is, if you take twice the first, plus 3 times the second, plus 4 times the third, you're going to get 13. And the third clue is, if you take 3 times the first, plus 4 times the second, plus 6 times the third, the answer is going to be 20. Now, can you see how difficult this would be to try to guess just from this information? The amount of wisdom that it would take to look at this and say, oh, x must be 2, y must be negative 1, and z must be 3. It's not that easy. However, what we're going to do is to take the system that we learned before and apply that to this system over here. See, what do we already know how to handle? Don't we already know how to handle 2 equations and 2 unknowns? What we're going to do over here is we are going to find a common denomination for the multipliers of x. See, what do 1, 2, and 3 all go into? They all go into 6. So watch what the strategy is going to be. I'm going to multiply the whole top equation by 6. You see what that's going to do? 6 times x, that will give me a 6x up here. I'm going to multiply the whole second equation by negative 3. Because if I do that, that will make this a negative 6x term. See, there'll be a 6x up here. There'll be a negative 6x down here. I'm going to multiply the bottom equation by negative 2x, because 3 times 2 is 6, so 3 times negative 2 would be negative 6. Now, do you see what's going to happen over here? I'm just symbolically writing this over here, what I'm doing. Now, what's going to happen when I do this? Let's just take a look and see what happens over here. You see there's going to be a 6x here, a negative 6x here, and a negative 6x here. So if after I do this, I now replace, I leave the first equation alone, but I replace the second equation by the first plus the second, you see the x term is going to drop out. If I replace the third equation by the third plus the first, the x term will also drop out again. And let's just see what happens if I do that. So let's actually go through and multiply it out. Multiplying the whole top equation by 6, we wind up with 6x plus 6y plus 6z is 24. Multiplying the whole second equation by negative 3, we get negative 6x plus negative 9y plus negative 12z is equal to negative 39. And multiplying the whole bottom equation by negative 2, we get negative 6x plus negative 8y plus negative 12z equals negative 40. Tedious, but not difficult. And in fact, computers can be set up to do these operations very, very quickly. Now what we do is we leave the top equation alone. See, 6x plus 6y plus 6z equals 24. Now we replace the second equation by the second plus the first. See, the 6x and negative 6x drop out. 6y plus negative 3y is negative 3y. 6z plus negative 12z is negative 6z. And 24 plus negative 39 is negative 15. The important thing is what? There's no longer an x term over here. Now let's replace the third by the third plus the first. The 6x and the negative 6x drop out. 6y and negative 8y is negative 2y, right? 6z and negative 12z is negative 6z. And 24 plus negative 40 is negative 16. Again, what's happened? No x term over here. Just look what we have over here. See, what do we have here? We have what? We've taken 3 equations and 3 unknowns, and by using the same technique that we used before, we effectively reduce it to what? 2 equations with 2 unknowns. I'll just get back to that in a minute over here. See, what I want you to see over here, what happened is this. See, we started out with 3 equations with 3 unknowns. Look what I just circled over here. Aren't the only 2 unknowns here, y and z? And by the way, I can simplify this. You see, what I can do is I can multiply both sides of the second equation by negative 1/3. That's the same as basically canceling -3 from both sides. You see, negative 1/3 times -3 gives me +1. Negative 1/3 times -6 gives me +2. And negative 1/3 times -15 gives me 5. So the second equation can be rewritten as y plus 2z equals 5. And now if we multiply the whole bottom equation by -1/2, the negative 2y becomes +y, the negative 6z becomes +3z, and the negative 16 becomes +8. And now what we've shown is what? That the system of equations that we started with is equivalent to this system over here. By the way, all I did over here was put this equation back into its original form. See, in other words, another way of doing that was what? I multiplied both sides of this equation here by 1/6, and that brings me back to the original form, x plus y plus z equals 4. The only reason that 6 was in here was to set this thing up so I could conveniently eliminate the x's from all but the bottom equation. By the way, notice that since the multiplier of y is the same in both of these, if I subtract the second equation from the third, the y's will drop out. See, y minus y is 0, 3z minus 2z is z, and 8 minus 5 is 3. That now tells me what? That z is 3. By the way, look at the pyramid that I've built over here. Look what happens. See, I know what? That x plus y plus z is 4. I know y plus 2z is 5. Now I know what? That z is 3. Watch what I can do now. Knowing that z is 3, can't I put the value of 3 back into the middle equation and solve for y? And once I know what z and y are, can't I replace z and y in the first equation by their values that we know they equal to and solve for x? See, for example, if z is 3, replace z by 3 over here, you get what? Y plus 2 times 3 must equal 5. That says y plus 6 equals 5. That says y equals -1. And once z is 3 and y is -1, just replace z by 3 and y by -1 over here, and you have x plus -1 plus 3 equals 4. That says that x plus 2 is 4, and that says that x is equal to 2, and now we've solved that equation. By the way, just to show you that we don't have to start with something we've already done, here are 3 more equations and 3 unknowns that make use of the fact that I haven't told you what the answers are in advance. See, I'm looking for 3 numbers such that when you add the 3 numbers up, the answer is 1. I also want what? Twice the first plus 5 times the second plus the third to be 5, and 3 times the first plus 4 times the second plus 2 times the third to be 2. And again, what do we notice over here? The common denomination here would be 6, so we could do what again? Multiply the whole top equation by 6, the whole middle equation by -3, and the whole bottom equation by -2. And I see our time is almost up, so I'm going to go through this one fairly rapidly. I'm just going to leave this picture here and just let you zero in on that and see how the steps just follow. Let me just bring you down to this step over here. See, having done this, what can I do? Replace the second equation by the first plus the second. That knocks the x term out of here. Replace the third equation by the first plus the third. That knocks the x term out of here. That leaves me with what? 2 equations on 2 unknowns. I can then solve for y and z, because I already know how to solve 2 equations on 2 unknowns. Once I know y and z, I can solve for x, and the details are left over here. But in the minute or so that I have left, I want to show you that sometimes these situations also can backfire. You can also give contradictory information. So I may have to go through this a little bit fast because I misgauged the time a little bit, but let's just see what happens over here. Here are 3 more conditions I give you. I tell you the first number plus twice the second plus 3 times the third is 6. I also tell you that 4 times the first plus 5 times the second plus 6 times the third is 12. And 7 times the first plus 8 times the second plus 9 times the third is also 12. Now again, the common denominator here is going to be 28. So I'm going to multiply the whole top equation by 28, the next equation by -7, see, because the 28 and the -28 will cancel when I subtract, and the whole bottom equation by -4. When I do that, look what I wind up with. 28x plus 56y plus 84z equals 168. -28x plus -35y plus -42z equals -84. And finally, multiplying the bottom equation by -4, we get -28x plus negative 32y plus negative 36z equals negative 48. Now we do the same thing we were trained to do before. And what was that? To replace the second by the first plus the second, and to replace the third by the first plus the third. You see, if we do that, what's going to happen over here? The first plus the second becomes 21y, right, plus 42z equals 84. The first plus the third, these drop out. 56 and negative 32 is 24y plus 48z equals 120. That looks like this. And when we want to solve this, we say what? Let's see, to solve this equation, let's reduce this first. Let's multiply both sides of this equation by 1 over 21. In other words, we're going to divide by 21 on both sides here, and we're going to divide by 24 on both sides here. That's going to give us 21 divided by 21 is 1, 42 divided by 21 is 2, and 84 divided by 21 is 4. Okay? And we wind up eventually with what? Y plus 2z is 4, but also that y plus 2z is 5. And now when we subtract, we wind up with what? 0 equals negative 1, which is never true. Let me just conclude by showing you what crazy thing happened over here that might not have been obvious, and in more advanced algebra, I'll show you how you could have discovered this, but for the time being, let me just show you something. Suppose I was to double both sides of the second equation. Wouldn't that give me 8x plus 10y plus 12z equals 24? And suppose I now subtracted the first equation from that. See, 8x plus 10y plus 12z is 24. Now I'm going to subtract x plus 2y plus 3z equals 6. If I subtract that way, what happens? I get 8x minus x is 7x, 10y minus 2y is 8y, 12z minus 3z is 9z, and 24 minus 6 is 18. What this says is, once the first two equations are true, what must have happened? It must be that 7x plus 8y plus 9z has to be 18. What did I say in this problem? I said 7x plus 8y plus 9z has to be 12. How can the same number be 12 and 18 at the same time? You see, what happens is we still have to worry about what? Inconsistencies. But the more variables we have and the more complicated the relationships, the easier it is to get tricked. And so that's part of the problem. Now, the other question you may ask is, where do these linear systems come up in the real world? And the answer is usually in problem solving. So what I'm going to do is stop for now, and in our next lecture, I'm going to introduce the question of problem solving. In other words, how to handle word problems, which always scares people. But until that time, study hard, have fun, stay young. See you next time.